We are on lesson 1 of chapter 9, which we're going to graph y equals ax squared plus c. First we're going to graph y equals a times x squared. Then we're going to graph y equals ax squared plus c. Then we'll solve a real-world problem. So in this chapter we're going to work with quadratic functions. A quadratic function is a nonlinear function that can be written in the standard form y equals ax squared plus bx plus c. These kind of functions create a parabola shape, which you can see is a curved line which bends evenly. The most basic of all quadratic functions is the one that's shown here, y equals x squared. It's often called the parent quadratic function, because you can use it to compare it with other functions. Each parabola that we do create has a vertex. A vertex is the lowest or the highest point on a parabola. It's the point where it stops going down and it starts going the other way. And since parabolas are even, meaning they go down and up at the same rate, there is an axis of symmetry. The axis of symmetry passes through that vertex and divides the parabola in two. For this parent function, the axis of symmetry is at 0 for x, but sometimes it's over to the right or the left depending on the function. Let's try graphing some of these functions. So it says graph the following quadratic functions. Compare them with the graph of y equals x squared, or that parent function. So we already have the parent function graphed here, as best as I could, obviously. So let's graph this one, y equals 3x squared. Let's do this one in blue. So we can use a table to graph these. We can have x over here and y over here. I like doing -2, -1, 0, 1, and 2. So we could plug in numbers for x and get an output of y. So if we look at this here, we have -2 squared, which is +4, times 3, which is +12. -1 squared, which is +1, times 3, which is +3. 0 squared is 0, times 3 is still 0. 1 squared is +1, times 3 is 3. And then 2 squared is 4, times 3 is +12. If we plot these ones out, this will be a little bit difficult with our graph. We'll make an attempt. -2 and +12 we'll say is right here. So +2 over here, you'll notice, is also +12. We have +1 and 3 and -1 and 3. And then 0 and 0. So as you'll notice, here is our new parabola. So we're supposed to compare it to the parent one. And what do you notice about this? Well, I notice that it's multiplied times 3. So what that does is the parabola goes up from the axis of symmetry on both sides much more quickly. And that makes sense. This 1 becomes a 3. This 4 becomes a 12. The 0 obviously remains the same. But you notice that it's just going to be rising that much more quickly. Let's do the same thing for this one. We'll do this one in purple. So when we have -2, -1, 0, 1, and 2. When x is -2, we square that to make it +4, times -1/4 would be -1. -1 squared would turn into +1, times -1/4 would just be -1/4. 0 squared is 0, times -1/4 is still 0. +1 squared is +1, times -1/4 is -1/4. Then 2 squared is 4, times -1/4 is -1. So let's plot this one out. We have -2 and -1. -1 and -1/4. Let's be precise on that one. That looks pretty good. Then we have 0 and 0. 1 and -1/4. And we have 2 and -1. So if we plot this parabola out, we can start at 0 and work our way out here. Starting at 0, work our way out here. Now this isn't perfectly drawn, but we can get a pretty good idea of what this is supposed to look like. Here we have the parent function, which looks like this. Since we're multiplying it times a negative, you notice that it's upside down. It flips it. And then we notice that this is a wider parabola, or it's not decreasing at the same rate as the parent function is. And that's because this 1/4 is less than 1. So it's going to decrease the rate of change in this parabola. Now we can graph ax squared plus c. So what is this c going to do to our parabola? So let's graph these following functions to compare it to that parent graph. We have y equals x squared plus 5. So if we do this in blue, we have x and y. Let's do the same, negative 2, negative 1, 0, 1, and 2. So when x is negative 2, negative 2 squared is 4, plus 5 is 9. Negative 1 squared is 1, plus 5 is 6. 0 squared is 0, plus 5 is 5. 1 squared is 1, plus 5 is 6. And then 2 squared is 4, plus 5 is 9. So as I plot these out, I have negative 2 and positive 9 around there. Negative 1 and positive 6. 0 is 5. 1 is positive 6. And then 2 is positive 9. So here I'm going to graph my parabola. And I'm not sure if you can notice this, but this looks like it's the exact same parabola as this one. And that's because the slope is the same. We have just x squared and we have x squared. What's different here is this y-intercept. When x is 0, y equals 5. So this is actually just the same parabola shifted up 5 spots. So everything is just going to be 5 more than the previous one. Here we have positive 1/2 times x squared minus 4. So if we do x and y with negative 2, negative 1, 0, 1, and 2, negative 2 squared is 4 times 1/2 is 2. 2 minus 4 is negative 2. Negative 1 squared is 1 times 1/2 is 1/2. 1/2 minus 4 is negative 3.5 or negative 3.5. 0 squared times 1/2 is 0 minus 4 is 4. 1 squared is 1 times 1/2 is 1/2. 1/2 minus 4 is negative 3.5. 2 squared is 4 times 1/2 is 2 minus 4 is negative 2. So if we plot these ones out, we have negative 2 and negative 2, negative 1 and negative 3.5, 0 and negative 4, 1 and negative 3.5, and 2 and negative 2. So let's try my parabola out over here, this curved line. A couple observations here. First, I have this negative 4, and just like this positive 5 moved this one up 5, this negative 4 moved this parabola down 4. It's still a positive slope, so that's why it's still pointing up here. But we notice that it's a 1/2 instead of the regular x squared, or 1 for the slope. So it's going to open up much more slowly to the left and the right as you compare that to the parent function. Let's do a real-world problem. It says a solar trough has a reflective parabolic surface that is used to collect solar energy. The sun's rays are reflected from the surface toward a pipe that carries water. The heated water produces steam that is used to produce electricity. The graph of the function y equals 0.09 x squared models the cross-section of a reflective surface where x and y are measured in meters. Use the graph to find the domain and range of the function of this station. So this is what it's asking us to do here. Use the graph to find the domain and range of the function of this station. So we're looking for domain and range. Just an observation that I have, when you have that parent function, you notice that parabola opens and closes really quickly. Since this is such a small number, 0.09 times the x squared, you'll notice that this parabola opens very slowly. As we're looking for the domain and range, remember these are the x values and the y values of this parabola. So if we're looking for x values, I see that we're counting by ones here, then this 3 is right here. So the greatest this x value could be is 5. The smallest our x value is negative 5. So D for domain, negative 5 is less than x, or equal to, I guess you could say, which is less than or equal to positive 5. Our range then, looks like the lowest our range goes here is 0, and the highest it goes, this looks like 2 and 1/3, and it's the same thing on both sides. So if we say range, in this case, R for range, we would say 0 is less than or equal to y, which is less than or equal to, and we'll say 2 and 1/3. This could have been a little bit off, but that's kind of what it looks like to me.